Okay, hello everybody. We're going to talk about partial derivatives today and see that they are nothing new. It's just a special case of the derivative we already learned. You might see symbols like this, or this, or this. And this little curly thing is like a curly D. And in LaTeX, you literally type /partial and they'll give you this symbol. Or in Julia, you can type /partial and it'll give you this symbol. And so the way we read it is, like this symbol here is partial x, like partial over partial x, but people just say partial x, partial y, partial z, sort of like they'd say d by dt or d by dy for the derivative in single variable calculus. Now they say partial x. And what is it? Well, let's say our input space is two-dimensional and we just move in the first dimension, then that's what partial x is. It's the derivative of our map f at a point in the first dimension. Okay? Partial y is the derivative of our map f at a point in the second dimension. Partial t is the derivative of our map f at the point p in whatever dimension was labeled t. So normally people write the first one as x, the second one as y, and then maybe the third one is z, and that would be partial z. And maybe the fourth one is t, so it might be like this, but it just depends on what you labeled your input space. So these are the labels for one of the dimensions in the input space of a map. If you want to write the map, you can write it up here. So we'd say the partial of f with respect to x, the partial of the map f with respect to y, the partial of the map f with respect to t. So we've named one of the inputs t, and we've named one of the inputs y, all these kind of things. It's best to see examples. So let's just compute examples. Here's a map. It gives something called the Whitney umbrella. Maybe I have a picture. Yeah, here it is. This is what that map looks like. It's this Whitney umbrella. And so here's the map. Let's call it F. Well, then what is partial f partial u? Well, we named one of the variables u, or one of the inputs u. And so maybe what you can mean, well, f has three outputs. So what do? Well, actually, we take sort of partial u of the first component function, partial u of the second component function, and partial u of the third component function. I normally would never write all this. But then what are these three things? Well, the partial here, you just differentiate with respect to u, and you treat the other variables as if they were constants, like the number 4 or the number -18. And so, what's the derivative of 4 times u? It's 4. What's the derivative of v times u? It is v. The derivative with respect to u of the function that is just u in single variable calculus, we learn that is 1. Here, the derivative with respect to u of a v squared, well, it doesn't even have a u. So v squared is constant. Maybe it's 4 squared is 16. So the derivative of 16 is 0. And so this is our answer. This would be partial u. It's sort of a vector with 3 functions. 2 of them happen to be constant. Then what's partial the other input variable? I guess we called it v. So this should, again, because the output had 3, we should also have 3 things. We take the partial v of this, and we get u. Okay? And so now the partial v of this one gives us 0, and the partial v gives us 2v. Okay. And yeah, so there's one example. So you see that partial derivatives are pretty easy because you just have to think about, well, which variable am I allowing to change and then treat that as if you're in single variable calculus and ignore all the other variables. Treat them as constants. Let's see this in another example. This one is too much, so I'm going to do a different one. How about this? Well, I don't know. Let's do this one. Here's our parameterization of the circle. Okay, the input is called theta 1. So what's partial f partial theta 1? Well, it needs two outputs, and so the first one is the derivative of cosine is minus sine theta 1. This is just like single variable calculus. Derivative of sine is cosine. So that's partial f partial theta 1. Okay, let's try this one. Here, this is parameterizing the sphere. So let's do partial f partial theta. Well, I have two inputs. I could say partial theta 2. Or no, let's do partial theta 1 again. Okay. So this is a constant because we're partialing with theta 1. So this is a constant. It's like 4. And so it's just negative sine theta 1 times the constant. Here, we take the partial with respect to the first variable, and we get, well, the derivative of that is minus sine theta 1, and then this is a constant, so it just hangs out. Here we get cosine. Okay. Now what's the partial f partial theta 2? We can do that. There's the second input variable. We can always differentiate with respect to a movement, and this is a movement in the second dimension. When we did partial theta 1, that was a movement in the first dimension. And this is the theta 1, theta 2 input space plane. Okay? And so we can calculate this, partial theta 2. Okay, now these are variables, and they'll get differentiated, and these are all constants. They just hang out. Derivative of cos is minus sine. Derivative of sine is cos. The constant hangs out. Derivative of this is 0. Excellent. So I hope you're seeing that we can compute partial derivatives. And the biggest thing about them is just this more notation. They are really just the derivative in the first dimension, or maybe it's the second dimension, or maybe it's the fourth dimension. It just depends on what order we labeled and how we labeled our inputs. We always take the derivative with respect to one of the inputs, the input variables. And so like here, we could take the derivative in this direction, which would be partial theta 1. Okay. There's another kind of way you'll see people write this. So let's look at this function, and let's just view it as its own sort of expression over here. And you might see people say d theta 1 of this. Okay, and then you would say equals, well, minus sine theta 1 cos theta 2, because this is a constant, so it just hangs out. And you might see people write this, so I'm just pointing it out to you that you can view this taking the derivative of this expression gives another expression, okay? And then what we did is when we had maps and they had 3 component functions, we just did that 3 times and arranged them again in a 3-dimensional vector. Okay. Another thing you might see people do is you might see people give names to things, like they'll say g is cosine of theta 1, cos of theta 2. And then they'll say dg, d theta 2 is, and then the answer would be, well, this is a constant because we're differentiating with respect to theta 2. So that just hangs out. Now this one becomes minus sine theta 2. Okay. And so you might see this sort of, this sort of notation as well. Okay. Especially in partial differential equations, because the function is often the unknown thing. And so you wouldn't have an expression for it. You would just write the function everywhere as a symbol and then take various partials. Now, in this case where we had g is this, what do you think would this be? I could write a g there, or we could write the g here. Either way, this is just notation. It's really silly that we need to write all these things to mean just take another derivative. Take another derivative with respect to theta 2. So we took one derivative here. This was partial theta 2. And we will take another derivative, partial theta 2. And so the derivative sign is cosine. And this is a constant in terms of theta 2. This is just a number that has nothing to do with theta 2. So it just hangs out. Okay? And so we can keep taking derivatives, partial theta 2, forever and ever. And then we would get like d3 d theta to the third. This is ridiculous notation. In my opinion, it shouldn't be a theta 3. There was no theta 3, right? We only had 2 input dimensions, so there just wasn't a theta 3, so I made a mistake. I meant this 3 up here, and they would write theta 2. Now, this is ridiculous because we just had 2 inputs. What was it? Theta 1 and theta 2 going somewhere. And so why don't we just refer to the first dimension and the second dimension? And I would write this. I would much prefer the notation second dimension to the third power. That means take the partial derivative in the second dimension, which happens to be named theta 2, but could be named other things, like y is often the second dimension, and do it 3 times. This one here would then be, in this notation, take the derivative in the second dimension and do it twice. Do that to g. Okay? And then this one here, just the one partial derivative, would be take the derivative in the second dimension once. Okay? So in this notation, if g is cos theta 1, cos theta 2, then partial 2g would be take the derivative in the second dimension, which means we get a negative sine theta 2, and the constant hangs out. Okay. I have been showing many examples of sort of just working with this notation, but I just really want to say, like, you know how to do this because you took single variable calculus. And so the only thing is that there's all these notations, and that's the thing that makes it tricky. But just when you think to yourself what's really going on is we're moving the input space either in the first dimension or in the second dimension or in the third dimension if we have 3 input dimensions. And so really we're just taking the derivative in that direction, in the second dimension, in the fourth dimension, whatever it is. And then, I mean, the reason these are nice is if we only change one of the dimensions, then we can calculate it. We can calculate it so easily like this, where we look at this and we say, well, I'm only changing in the second dimension, so I can treat anything that involves the first variable as a constant. And then we're back to single variable calculus, okay? So maybe I'll record that. I mean, partial derivatives are just derivatives in one of the dimensions alone. Derivatives where we move purely in one dimension. That makes it easier to calculate because we can treat the others as, this is easier since all other input variables are treated as constants, like scalars. They play no role in taking the derivative. And so what that means is that we're back in single variable calculus. We're back in single variable calc. Okay. So that's why partial derivatives are quite nice. But, you have to deal with things like this ridiculous notation that you'll see everywhere. And of course, you can make up your own notation, like this is pretty nice. And we have one unifying notation, which is this. And this will actually be important because sometimes you need to move not perfectly and purely in one of the coordinate directions, right? Okay, so for machine learning, for chemical reaction networks, for planetary motion, we have to move in a certain direction. You'll see this later. It will not be one of these perfect movements, sort of these easy movements. It will not be that. And so that's why we really do need to know this notation, which is, a special case of it is this partial derivative in the first. This notation means it's the partial derivative in the second. But in general, we'll take the derivative of a map f at a point, will be a linear map, and we'll evaluate it in some direction v, some movement direction. And that movement may not be perfectly in E1, it may not be perfectly in E2, it may be some combination of E1 and E2. Okay, good. So take a look at this friendly zoo of surfaces and see if you can calculate the partial derivatives. For example, of the Klein bottle in the bagel immersion, according to Wikipedia, which looks like this. You could do this in GeoGebra. That would be fun. So you can just, find this formula. Okay, everybody, that's partial derivatives.